And difference value we are calculating the value by using the neighboring points over there. So these are the FDM. So that's for this I will have to calculate the differential equation in terms of difference of the values. But in FEM, I will show you some important tools that the finite element has its origin in the field of structure analysis. So initially they are using for the structural analysis for the bridges and everything. So this FEM journey started to solve the derivatives problems, and then we played this solving derivative for Maxwell's solution of the Maxwell's by using FEM technique. So the systematic generality of the method makes it possible to construct the general purpose computer programs for solving the wide range of problems. So in simplified way, I will show that how the FEM is important to calculate the circumference circle. So in finite element method, there is finite elements are there, nodes are there, the terminology they are using. Suppose I would like to calculate the circumference of circle. I can divide the circumference of circle into small element 1, 2, 3, 4. These are the elements, and elements meet at the point is called node. So this circumference of circle I can calculate by using the analytical formula also. So I know the radius, so it is 2 pi is my circumference circle. But in FEM, I will take the different methods to calculate the linearized method. So I divide the circumference circle into small element 1, 2, 3, 4, 5. Now, it's coming directly here. Okay, so this is something like some other, but in this circumference circle, I can divide these elements into the, suppose small elements here, they can divide this circumference circle into small element, and I will find out the radius of this point, and this radius of points from this point, and get the perpendicular over here. So first step in the FEM is the discretization of the entire domain into small element, then finding out the governing equation for each element, and then assembly of every element. So this slide so this circumference circle is there, and the circumference circle is divided into circumference into small element, and these elements meet at a point is called node. So I can divide this circumference circle into uniform elements or non-uniform elements. So first step is the discretization. Second step is the finding governing equation for each and every element. So this is I can draw the perpendicular here. So it will come in the sine theta e by 2 times, because he is the actual length. So element length he. So actual length is se. So he minus se is my error over here. I can add, if it's uniform, I can add all the elements size, so that it will form the. Now, if it is uniform mesh, it's n times uniform, so it will take the 2r sine pi by n for all elements summation statement. So first step in the FEM is the discretization, second one is the element equation, third is the assembly of all equations. So this is the exact solution for circumference circle. This is an error over here. I can reduce this error if n tends to infinity. If you form the number of elements very high, then it is possible to reduce the error, because so this is for 5 elements. If I use 10 elements, it's 1, 2, 3, 4, 5, 6, 7, 8, 10. That time this error is very small. So ideally it should be n tends to infinity. So practically it will take a long computation time. So this problem is for the exact solution. This is the error. We can reduce it n tends to infinity. So the error is 2 r times or 2 pi r by n minus 2 times sine by n. So if n tends to infinity, mathematically suppose x is 1 by n. So limit n tends to infinity means limit x tends to 0. So this is the 0 by 0 form. So like L hospital will take the derivative on numerical and denominator, will get the exact solution. So where the condition is only n tends to infinity means if you are increasing the element number, I can get the accurate results. But increasing element numbers means increasing the size of matrix. So once this is increased, so I'm taking the inverse of that, again the size computation time will take a lot of times. So practically, in the analytical way, 2 pi r is there, and finite elements also will get the same results with the approximations. Getting? So there are some summaries over here. I would like to solve this Laplace equation by using a FEM finite element method. So x and y axis over the geometries are divided in non-linear shapes. And these are the elements over there. So I divide this geometry into small elements. So these are the elements where the global nodes are there and elements numbers are there. So actual boundary conditions like this, and these are the boundary conditions over there. The number of nodes are there. So in the Sadi Q book, it's reported so many names of the equations like homogeneous wave equation and the partial differential for variation principle. So these are the Laplace equations and these are the variation principles for that. So this previous equation we can solve, the partial differential equation we can solve using the FEM, and in this technique I will show the systematic way that how the FEM will play the important role. Suppose I have geometry of 3 nodes, that is 3 nodes are there, V1, V2, V3 are nodes are there. Based on this polynomial equation, suppose V1 is equal to A plus Bx1 Cy1, V2 is equal to A plus Bx2 Cy2, V3 is equal to A plus Bx3 Cy3. So this is the transformation matrix for this. So A plus Bx1 plus Cy1, A plus Bx2 plus Cy2, A plus Bx3 Cy3. So I will take this. So this is a geometrical values. These are the node points where the values are there. These are the unknown coefficients. So I would like to calculate the unknown coefficients. I can take the inverse of this. So I'm just shifting this transformation matrix to the right hand side. So A base is equal to the inverse of these parameters, and the inverse of parameters is reported over here like this way with respect to the node values. So we are calculating the values of V1, V2, V3 with respect to the particular matrix which is the inverse of this one. So we are taking adjoints and determinants over there. So A is the actually area of that elements. If you are taking triangular elements over there, so there are 3 elements are there. So this actually this simplified form of this equation can be represented in the shape function. The shape function is the triangulars are there. So we are fixing 1 and 2 nodes and we are moving the another nodes. So that time alpha 1 is calculated. So in the third node say 1 and 2 as fixed, and third we are moving. So this variation is nothing but the shape function variation over there. So like this. So this triangle is there, x and y. So 1, 2, 3, V1, V2, V3. So 1, 2, 3 is there. Since it's a global local coefficient numbers, it's going anti-clockwise. If you go the clockwise direction, the results will be the same, only negative signs over there. And this inner matrix are there with respect to the coordinates over there. So I'm talking about this shape function, like this one, 1 and 2 is fixed, 1 and 2 is 2 and 3 is fixed, and this is the 1 point is variable. So alpha functions, shape functions are there. So for alpha 1, alpha 2, alpha 3. So these are the shape function variations. So we have to work with the simplified V1 is equal for 3 nodes. So I is 1, 2, 3, alpha I, x, y, I. So these are the energy equations over there. And we are forming the local coefficient values with respect to the shape function. So this is the local coefficient values over there. So this local coefficient values will form at this stage, and this local coefficient matrix combinations will be represented over here with respect to the positions 1, 1, 1, 2, 1, 3, 1, 3, 4, 2, 3, 3, because 3 nodes are there, 3, 1, 3 matrices are there. So in simplified way, the element coefficient matrix will directly in terms of the coordinates and the area of matrix, area of the cell, area of the elements, and these are the equivalence points over there. These points are equal and the values. So these values will form at the element-wise coefficient matrix formations. Suppose I can say, suppose this is high voltage plate is there, this is low voltage plate is there. So this high voltage plates and low voltage plates, we are given some boundary conditions, and 1, 2, 3, 4, 5 are the global coefficient nodes, and 1, 2, 3, 1, 2, 3 are the, you can say, element coefficient number. 1, 2, 3 are the elements number. So I divide this geometry into 3 elements with the 5 global nodes. So these 5 global nodes are there. So we give the 5 global nodes, we give the this 5 global nodes give the size of matrix is 5 by 5, because suppose at this point C11 is the position of this point, so it is C11 of first element plus C11 of second element. So it's coming here. So at the second point it is C12, so 12 means 1 3 of first element. So that's why it's 1 2 of 1 3 of first element. Similarly, the third position is the C1 3.